So in this section, we'll build the all-pass filter using JFET. Let's get started. So this is what is my all-pass filter structure, and let me give some component values here. So basically, I have created a plus minus 12 volt power supply for the op-amp here, and then I've created a low frequency oscillator which is swinging between 0 volt to minus 1.5 volt at 100 hertz frequency sinusoid. And let me just simulate some guitar input. So let it be a sine wave with 0 offset, an amplitude of 500 millivolt, and having a frequency of 1000 hertz. So this comes here. So this simulates my guitar input. Let me just give this signal a name. Let's say input. And let me call this as output or output 1. Okay. And let's give some values to these resistors. So this. So I hope you have understood the circuit by now. What I'm trying to do here is that this JFET is being modulated by this LFO, low frequency oscillation, and this will make the resistance of this JFET vary as per the sine wave. And this resistance of JFET is in parallel with R3. So the net effect will be that the parallel combination of R3 and JFET will start fluctuating in accordance with the LFO signal. So let's just run this simulation once so that we know everything is working fine. So let me run it for say 100 millisecond. Let's go ahead and run it. So firstly, let's see whether our input is getting generated correctly. Brilliant. So here we have a 500 millivolt signal swinging plus 0.5 volt minus 0.5 volt. This emulates a guitar input. And let's see what is the LFO. Great. So my LFO is a signal which is swinging between 0 volt and going to minus 1.5 volt. So basically, I'm reverse biasing this gate with respect to ground as per this sine wave. And because of this voltage, this LFO voltage, this resistance here will vary, and the current through this JFET will vary, and which is exactly what we want to do to make it a variable phase all-pass filter. And lastly, we'll see the output here. Amazing. So let me just change the color first. Okay. So as you can see, my output is phase shifted, and it is phase shifted in accordance with the modulation frequency, that is LFO. As you can see, the phase difference here is quite less, and the phase difference here is quite large, indicating that the phase is getting modulated because of the changing VGS, and hence the resistor here is changing. So what we can do here is, in fact, we can plot it for a longer duration, let's say for 1 second. So let's monitor a few cycles here. So you can see when the VGS is becoming 0, the phase difference here is quite large. At this point of time, this JFET has become a perfect short, and that's the reason why the resistance has reduced here. And when this VGS goes down and touches low voltage, then this acts as an open circuit, and the entire resistor is appearing across this terminal, and hence the phase difference here is different. So here you can clearly see my red signal is the LFO, which is going from minus 0.75 volt up to 0 volt, and then on the negative side it is going to minus 1.5 volt. So basically it is modulating the phase of the all pass filter. My green signal is the input, and my magenta signal is the output. So if you notice, when LFO is at its peak, that means when it is touching 0 volt, the phase difference between green and magenta is quite large. And when this LFO is at trough, the distance between this magenta and green wave is low, signifying that phase modulation is taking place because of this low frequency oscillation signal that I have applied on the gate of the JFET. We can also have a look at another plot here. Let's say I want to monitor my LFO. So I want to monitor my LFO. Let's give it a red color. And I also want to monitor the current through the drain. So here is the drain, and I want to monitor the current, and something very interesting is happening here. So let's just see. Amazing. So what you see here is, let me just, yeah, okay, now it's clear. So my red is the LFO voltage, which is swinging between 0 volt to minus 1.75 volt, and when it touches 0 volt, the current IDS increases, and then at some point of time, when the LFO voltage drops down, this JFET goes into the shut-off mode, hence no IDS is passing through it. Again, when the LFO voltage rises, the current through it starts to rise, and then once again it goes into a shutdown stage, effectively showing that this JFET is working as a variable resistor. So that's another way of looking at it. Right. So I can also do one thing. I can do FFT of this. I don't want to see the magnitude plot, so I will disable it. Let me first enable this axis, and let me just disable the magnitude plot. So now I'm only seeing, on the right hand side you can see the phase axis. The red is my output, the green is my input, and you can clearly see that the phase manipulation is taking place. So you can clearly see that at different frequencies, the phase of the output, that is red, is changing. So now what I can do is I can take my input signal and mix it with the output signal and see what kind of patterns they get generated. So for that I will design a mixer. Great. So this is my mixer where my input signal and my output one are getting mixed in equal proportion, and this will create a interference pattern in the output. So let me just, and this is just an inverting amplifier, nothing else. So let me just reduce this to 200 milliseconds. Let me run the simulation. So we have an input signal. We have first stage output of the all pass filter. This is phase shifted, as you can see. And what does this get us? The final output of the mixer. So you can see now you can see that because of this phase shift between the input and output, when they are getting mixed, there's a constructive and destructive pattern of output that is happening. So at some places, when the phases match, you see the output, the net output, its amplitude rises up, and then when the phases don't match, the amplitude becomes smaller. You can see it here. And this is how this signal is behaving in the output. And this creates notches in the spectrum of the signal, and these notches are the ones which give those swishing sound to the phasor effect. So this is a complete design and development of phasor on an op-amp circuit. Practically speaking, we will be using very low LFO frequency. In fact, this will be somewhere around 10 hertz or low, even, yeah, 10 is fine. So here you can clearly see that I am getting destructive and constructive pattern based on my LFO frequencies. So I hope you have understood how this whole circuit is functioning. How the circuit is acting as a variable resistor, giving phase differences to the input signals, and then the original signal is mixed with the phase modulated signal here, phase shifted signal here, and then the interfered pattern signal appears here as a output, which in frequency domain looks like notches in the spectrum. And so that's how this entire phasor effect works.